Black holes mislead our intuition because their most famous image is light from outside a boundary we cannot see. The event horizon, the defining feature of a black hole in classical general relativity, is not a material surface, not a wall, not an edge you could touch. It is a causal boundary, a one-way threshold in the structure of space-time itself. The darkness at the center of the Event Horizon Telescope's images of the supermassive black hole at the center of M87 is not the black hole emitting nothing. It is the result of photon capture and gravitational lensing, a brightness depression surrounded by synchrotron radiation from magnetized plasma at temperatures exceeding 10 billion Kelvin. The black hole information problem, the question of whether information that crosses the event horizon is destroyed, preserved, or encoded elsewhere, has driven theoretical physics for 50 years and remains unresolved. Competing frameworks, fuzzballs, firewalls, soft hair, entanglement islands, each propose radically different answers to what the boundary actually is, and each implies that the classical picture of a smooth, empty horizon around a dark singularity is incomplete. Horizon-scale observations from the Event Horizon Telescope, polarimetric monitoring from ALMA, and gravitational wave echo searches from LIGO, Virgo, and Kagra are now testing these proposals against data. What follows is a forensic examination of the evidence. By the end of this video, you will understand why the word black misrepresents what telescopes actually detect, why the word hole misrepresents what the theoretical physics demands, what the competing quantum gravity frameworks claim about the boundary, and where the observational evidence currently stands, including what it rules out and what it cannot yet distinguish. If this channel is the kind of content you return to, consider subscribing. For those who want to support this work directly, the link to our Patreon is in the description. The Observer tier gives you ad-free videos, audio-only downloads for offline listening, and a vote on future topics. There is no algorithm shortcut for depth. Let us begin with what a black hole actually is and what it is not. In classical general relativity, a black hole is not a hole in matter. It is not an opening. It is not a tunnel. It is a region of space-time whose boundary, the event horizon, is defined causally. Light-like and time-like trajectories from inside that boundary cannot reach an observer at infinity. The event horizon is a null surface, and its definition depends not on local physics, but on the entire future history of the space-time. Locally, for a sufficiently massive black hole, nothing singular occurs at the horizon. An observer crossing the event horizon of a supermassive black hole would not, according to classical general relativity, notice anything special at the moment of crossing. The tidal forces would be negligible, the crossing would be uneventful, and it would be irreversible. The mathematics that describes this boundary begins with Karl Schwarzschild. In 1916, while serving on the Eastern Front during World War I, Schwarzschild produced the first exact solution of Einstein's field equations for a spherically symmetric point mass. The solution contained a characteristic radius, now called the Schwarzschild radius, below which the escape velocity exceeds the speed of light. The equation is direct. R sub s equals 2gm over c squared. The Schwarzschild radius equals twice the gravitational constant times the mass, divided by the speed of light squared. G is the gravitational constant. M is the mass of the object. C is the speed of light. For every kilogram of mass, there exists a corresponding length scale. For the Sun, that scale measures approximately 2.95 kilometers, roughly 1.83 miles. For a black hole of 4 million solar masses, the Schwarzschild radius extends to approximately 12.7 million kilometers, or about 7.9 million miles. The diameter of the event horizon in that case would stretch to roughly 25.4 million kilometers, about 15.7 million miles, smaller than the orbit of Mercury, containing 4 million times the mass of the Sun. The idea of an object from which light cannot escape predates Schwarzschild and even Einstein. In 1783, John Michell, an English clergyman and natural philosopher working in the quiet parish of Thornhill in West Yorkshire, reasoned that a body sufficiently massive and compact would have an escape velocity exceeding the speed of light, rendering it invisible. Michell was not guessing. He was calculating. Using Newtonian mechanics and the corpuscular theory of light then prevalent, he estimated the size such a body would need to be and published his results in the Philosophical Transactions of the Royal Society. Pierre-Simon Laplace arrived at a similar conclusion independently in the 1790s, including the calculation in early editions of his Exposition du Système du Monde before later removing it, possibly because the wave theory of light, gaining favor in the early 19th century, made the corpuscular escape velocity argument less convincing. They called these objects dark stars. The reasoning was Newtonian, not relativistic, and the concept of an event horizon as a causal structure did not exist in their framework. In Newtonian gravity, light that escapes a dark star would simply slow down and fall back, like a ball thrown upward. In general relativity, the picture differs at its foundation. Light does not slow down. Space-time itself curves so severely that outward-directed photons are redirected inward. The Newtonian dark star and the relativistic black hole share a name and a superficial similarity, yet the underlying physics is entirely different. The event horizon is not a surface where light runs out of energy. It is a surface where the geometry of space-time no longer permits outward-directed trajectories to reach infinity. The core intuition, though, that mass could create a region from which light does not emerge was present more than 2 centuries ago. Think about that for a moment. The idea that something could be so dense that light itself cannot leave is older than the periodic table, older than the theory of electromagnetism, older than the discovery of Neptune. And yet, more than 200 years later, the question of what happens at that boundary and what lies beyond it remains one of the deepest unsolved problems in physics. The modern description of astrophysical black holes uses the Kerr metric, a stationary axisymmetric vacuum solution of Einstein's equations that describes rotating black holes. Nearly all astrophysical black holes are expected to rotate because the matter that formed them carried angular momentum. The Kerr metric is characterized by only 2 parameters, mass and spin. Charge is expected to be negligible for astrophysical objects. This serves as the baseline space-time used in virtually all observational interpretation, the framework against which the Event Horizon Telescope compares its data, and the geometry from which shadow sizes, photon ring positions, and accretion flow dynamics are calculated. In the Kerr geometry, matter orbiting the black hole cannot maintain stable circular orbits arbitrarily close to the event horizon. The innermost stable circular orbit, ISCO, defines a boundary inside which orbits become unstable and material plunges inward. The gravitational radius, r sub g equals gm over c squared, provides the natural length scale used in EHT papers. It measures half the Schwarzschild radius. When EHT reports angular sizes, They express them in units of gm over dc squared, where d is the distance to the object. For M87 star, the supermassive black hole at the center of the galaxy Messier 87 and the first black hole ever imaged, the mass reported by the EHT's 2019 analysis stands at approximately 6.5 billion solar masses. The Schwarzschild radius for this mass extends to approximately 19.2 billion kilometers, or roughly 11.9 billion miles. The diameter of the event horizon reaches approximately 38.4 billion kilometers, about 23.9 billion miles. To place this in perspective, the distance from the Sun to Pluto, at its most distant, measures approximately 7.4 billion kilometers. The event horizon of M87 star would extend more than 2.5 times the diameter of Pluto's orbit. The entire solar system, Sun, planets, Kuiper belt, could fit comfortably within the Schwarzschild radius of M87 star. And yet this region of space-time, larger than the solar system, is described by only two numbers, mass and spin. The angular gravitational radius of M87 star, gm over dc squared, measures approximately 3.8 plus or minus 0.4 micro-arc seconds, as reported by the EHT. This angular gravitational radius, combined with the observed ring diameter of approximately 42 micro-arc seconds, constrains the mass-to-distance ratio and provides one of the most direct tests of compact object spacetime geometry available. The ring diameter spans roughly 11 times the gravitational radius, consistent with the expected size of the photon ring in the Kerr metric, where strong lensing concentrates light from the accretion flow into a narrow annular structure at approximately 5.2 gravitational radii for a maximally spinning black hole, viewed from specific inclinations. This brings us to the first half of the title, Why Black Holes Are Not Actually Black. The phrase black hole suggests an object that emits nothing, a perfect absorber, a featureless darkness. The Event Horizon Telescope's images might seem to confirm this, a dark center surrounded by a bright ring. The dark center, though, is not the black hole radiating darkness. The dark center is a shadow, a brightness depression caused by photon capture and strong gravitational lensing. Photons that approach too closely are captured by the gravitational field and cannot reach the observer. The result is a region of suppressed emission in the image plane. The EHT's M87 star analysis reports that emission is suppressed interior to the ring by a factor greater than 10, direct evidence of a black hole shadow in the general relativistic sense. The ring itself, the bright crescent that became the most famous image in modern astrophysics, is not the event horizon glowing. It is synchrotron radiation from relativistic electrons spiraling in magnetic fields in the immediate vicinity of the compact object, gravitationally lensed and concentrated into a narrow annular structure. The synchrotron process drives the brightness. When relativistic charged particles, primarily electrons, move through magnetic fields, they emit radiation. The characteristic frequency of this emission is described by the synchrotron critical frequency equation. Omega sub c equals 3/2 times gamma cubed times omega sub b times sine alpha. In this equation, gamma is the electron Lorentz factor, a measure of how relativistic the electron is. Omega sub b equals qb over gamma m sub ec, where Q is the electron charge, B is the magnetic field strength, M sub E is the electron mass, and C is the speed of light. Alpha is the pitch angle between the electron's velocity and the magnetic field direction. The equation connects the magnetic field strength and the electron energy to the frequency of the emitted radiation. For the magnetic field strengths inferred near M87 star, roughly 1 to 30 Gauss, and for electrons with Lorentz factors in the hundreds to thousands, the characteristic emission falls in the millimeter and sub-millimeter bands, precisely the wavelengths at which the Event Horizon Telescope observes. The EHT does not photograph the event horizon. It photographs the synchrotron-emitting plasma near the event horizon, as shaped by gravitational lensing. The distinction matters because the image is not a picture of the boundary. It is a picture of the environment around the boundary, an environment that, as the data increasingly shows, is neither silent nor featureless. To understand what the EHT actually measures, consider the instrument itself. The Event Horizon Telescope is not a single telescope. It is a global network of millimeter wavelength radio observatories linked through a technique called Very Long Baseline Interferometry, VLBI. By combining signals from telescopes on different continents, from ALMA on the Chajnantor Plateau in Chile's Atacama Desert, officially inaugurated in 2013, to the South Pole Telescope in Antarctica, to facilities in Hawaii, Arizona, Spain, Mexico, and France, the EHT synthesizes an effective aperture approximately the diameter of the Earth. The angular resolution achieved is of order 20 micro-arc seconds, sufficient to resolve structures at the event horizon scale of both M87 star and Sagittarius A star. The images produced are not photographs in the conventional sense. They are reconstructed from sparse measurements of the electromagnetic field's Fourier components, the visibility amplitudes and phases sampled at specific baseline lengths and orientations. The reconstruction process involves algorithms, calibration procedures, and model assumptions. Different imaging pipelines can produce slightly different images from the same data. The ring-like structure, the crescent, the brightness asymmetry, the central depression hold stable across pipelines. The fine details do not. This matters for evaluating claims about what the images show. The broad features are data-driven, while the substructure depends on the reconstruction. The connection between what the EHT sees and the space-time geometry is mediated by general relativistic magnetohydrodynamics, GRMHD, the numerical framework that simulates magnetized plasma orbiting and accreting onto a black hole in full general relativistic conditions. GRMHD simulations produce synthetic images that are compared to the EHT data to infer plasma parameters, accretion state, and consistency with the Kerr metric. The process is indirect: observation, simulation, comparison, inference. The black hole is not measured directly. Its properties are inferred from the way its gravitational field shapes the emission from the surrounding plasma. The 2021 EHT polarimetric results for M87 star directly contradict the lay notion of a featureless absorber. The ring carries polarization, meaning the electric field vectors of the emitted radiation hold a preferred orientation, encoding information about the magnetic field structure and the plasma conditions near the compact object. The polarization is not uniform. It carries structure. It changes across the ring. The pattern traces a coherent spiral around the crescent that encodes the geometry of the magnetic field in the emitting region. The models that best fit the data are magnetically arrested disks, a class of accretion states where the magnetic flux near the black hole becomes dynamically dominant. In a magnetically arrested disk, the magnetic field reaches sufficient strength to impede the inflow of accreting matter. The field accumulates near the event horizon until it hits a saturation point where its pressure balances the ram pressure of the infalling material. The accretion becomes episodic, with magnetic flux eruptions periodically allowing matter to cross the field lines and reach the compact object. The accretion flow is not a smooth, steady process. It operates as an active, magnetically mediated negotiation between gravity pulling matter inward and magnetic pressure pushing it outward. The magnetically arrested disk state carries specific observational signatures in polarimetric images. The resolved polarization pattern, its spiral structure, its fractional polarization, its variation across the ring, provides constraints that other accretion states fail to match. In the GRMHD simulation library used by the EHT collaboration, magnetically arrested disk models consistently outperform weakly magnetized alternatives in reproducing the observed polarization morphology of M87 star. This is not a marginal preference. The data strongly favors dynamically important magnetic fields at the boundary of the compact object. The connection to relativistic jets is direct. M87 star powers one of the most prominent astrophysical jets known, a collimated outflow of relativistic plasma extending hundreds of thousands of light-years from the galaxy, visible at radio, optical, and X-ray wavelengths. The energy source for such a jet has long been theorized to involve the rotational energy of the spinning black hole, extracted through magnetic fields threading the ergosphere. The inferred plasma parameters from the 2021 magnetic field structure analysis prove striking. Electron densities of order 10 to the 4th to 10 to the 7th per cubic centimeter. Magnetic field strengths of 1 to 30 Gauss. Electron temperatures of order 1 to 12 times 10 to the 10th Kelvin, between 10 billion and 120 billion Kelvin. These are model-dependent estimates, inferred through simplified emission models and comparisons to simulation libraries. They paint a consistent picture. The boundary region of a black hole is not dark. It is a hot, magnetized synchrotron source with measurable polarization structure. The mass accretion rate inferred for M87 star from models consistent with the polarimetric data falls at roughly 3 to 20 times 10 to the -4th solar masses per year. To place that in context, M87 star accretes matter at a rate of roughly 1,000th to 1/50th of a solar mass per year. By astrophysical standards, this rate runs low, far below the Eddington luminosity, which sets the scale at which radiation pressure balances gravitational infall. The Eddington luminosity is given by L sub ed equals 4 pi g mm sub pc over sigma sub t, where m sub p is the proton mass and sigma sub t is the Thomson cross-section. For M87 star, with a mass of approximately 6.5 billion solar masses, the Eddington luminosity is enormous. The actual luminosity represents a small fraction of this. M87 star is, by its own standards, quiet. Even in this relatively quiet state, the boundary region produces structured, polarized, time-variable emission detectable across intergalactic distances. The Faraday effect adds another layer of complexity to what not black means observationally. As polarized radiation passes through magnetized plasma, the electric vector position angle, the EVPA, rotates. The rotation follows a wavelength squared law, chi equals chi naught plus Rm times lambda squared. Chi is the observed EVPA. Chi naught is the intrinsic EVPA at emission. Lambda is the wavelength. Rm is the rotation measure, a quantity proportional to the integral of the electron density times the line of sight magnetic field component along the path. The full expression, Rm, is proportional to the integral of n sub e times b parallel over the path length. The rotation measure encodes information about both the density and the magnetic field of the intervening plasma. It also means that the observed polarization structure is not a clean map of the magnetic field at the source. It is the source field filtered through Faraday rotation along the line of sight, which can scramble, rotate, or convert polarization modes. A 2023 EHT analysis detected evidence of circularly polarized emission on horizon scales in M87 star, an additional emission channel beyond total intensity and linear polarization. The inferred level remains low, with an image-resolved average circular polarization under a few percent, yet its presence is consistent with Faraday conversion processes in the magnetized plasma. This is not a static phenomenon. A 2025 multi-epoch EHT study reports that while the ring diameter of M87 star holds remarkably persistent at 43.9 plus or minus 0.6 micro-arcseconds across observations in 2017, 2018 and 2021, the total intensity and linear polarization vary across epochs. The spiral polarization pattern changes. In the 2021 observations, the helicity of the EVPA pattern changed, a signature that could reflect changes in the magnetized accretion flow or an external Faraday screen. This is the part that stays with me. Not because it is exciting, because it reframes everything. The edge of a black hole is not static. It is not silent. It is a time-variable, magnetically structured plasma environment whose polarization properties change on timescales of years. The Event Horizon Telescope is not photographing a fixed object. It is photographing an active process, frozen at the moment of observation and different each time it looks. Sagittarius A star, the compact object at the center of the Milky Way with a mass of approximately 4.297 million solar masses, tells a complementary story. The EHT's 2024 polarization results for Sagittarius. A star show the emission ring is highly polarized, with a prominent spiral EVPA pattern and a peak fractional polarization of approximately 40% in part of the ring. The precise mass determination of Sagittarius A star by Reinhard Genzel and Andrea Ghez, work that earned them the 2020 Nobel Prize in Physics, provides the foundation for interpreting these polarimetric measurements. 40%. In astrophysical plasmas, maintaining high fractional polarization is difficult. Faraday depolarization tends to wash out polarization signatures in strongly magnetized, dense environments. The interpretation paper treats this high polarization fraction as a stringent constraint, disfavoring models with too much Faraday depolarization and again finding a preference for dynamically important magnetic fields. A separate ALMA polarimetric observation of Sagittarius A star, taken during an EHT campaign, provides something even more specific. Following an X-ray flare, a sudden brightening detected simultaneously by the Chandra X-ray Observatory, the EVPA was observed to rotate with a time scale of approximately 70 minutes. The interpretation: equatorial orbital motion of a polarized synchrotron hotspot, a compact transient emission structure embedded in a magnetic field with a strong vertical component, viewed at a low inclination of roughly 20 degrees. Under a Keplerian orbital assumption, the inferred orbital radius sits at approximately 5 Schwarzschild radii. To appreciate what this means, consider the scales. 5 Schwarzschild radii for Sagittarius A star, with its mass of 4.297 million solar masses, corresponds to approximately 63.5 million kilometers, roughly 39.5 million miles. That distance falls at less than half the distance from the Earth to the Sun. At that radius, the orbital velocity reaches a notable fraction of the speed of light. The gravitational time dilation is measurable. The frame-dragging effects of the spinning compact object are non-negligible. Despite these extreme conditions, the hotspot maintains coherent polarization properties for at least one full orbit, long enough for the EVPA rotation to trace out a complete cycle in the ALMA time series. A 2024 Nature Astronomy study describes flares from Sagittarius A star as a frontier topic, discussing hotspot and flux tube models tied to magnetic reconnection, the process by which oppositely directed magnetic field lines snap and reconnect, releasing stored magnetic energy as thermal and kinetic energy of the plasma. Magnetic reconnection drives the same process behind solar flares on the Sun, yet in the environment near a supermassive black hole, the energy densities, magnetic field strengths, and gravitational fields are incomparably greater. The reconnection events produce compact luminous structures, hotspots, that orbit the black hole near the innermost stable circular orbit, emitting synchrotron radiation as they spiral inward or dissipate. These are not theoretical speculations. They are observed phenomena. ALMA detects the polarization rotation. Gravity at the VLTI tracks the orbital motion in the near-infrared. Chandra detects the X-ray flare that precedes the millimeter wave brightening. Multiple instruments observing at different wavelengths converge on the same picture. Structured, transient, magnetized emission at a few gravitational radii from the compact object. Not a dark, silent absorber. An active magnetized environment with detectable near-horizon structure. For those who value going deeper into these frontier topics, our Patreon supporters help make this level of research possible. The link is in the description. The Keplerian orbital period provides the connection. T equals 2 pi times the square root of r cubed over gm. T is the orbital period. R is the orbital radius, g is the gravitational constant, m is the mass. For Sagittarius A star, at 5 Schwarzschild radii, the Keplerian period falls at roughly 70 minutes, consistent with the observed EVPA rotation timescale. Full general relativistic corrections apply near the innermost stable circular orbit, yet the Keplerian approximation provides the right order of magnitude. What this means: a compact synchrotron structure orbits the black hole at a distance of roughly 5 event horizon radii, with polarization swings measurable in real-time monitoring. Not a dark, silent absorber. An active magnetized environment with detectable near-horizon structure. The Blandford-Znajek mechanism connects this magnetic environment to the relativistic jets observed in M87. The power scaling is schematic but informative. P scales like B squared times R to the 4th times omega squared over C. B is the characteristic magnetic field. R is the characteristic radius. Omega is the angular frequency. C is the speed of light. The mechanism extracts rotational energy from a spinning black hole through magnetic fields threading the event horizon, or more precisely, threading the ergosphere and the near-horizon region. The EHT's inference that near-horizon magnetic fields in M87 star are dynamically important and compatible with magnetically arrested disk states is directly consistent with the Blandford-Znajek process, powering the jet that extends hundreds of thousands of light-years from the galaxy's center. Roger Blandford and Roman Znajek proposed this mechanism in 1977. Nearly 50 years later, the EHT's polarimetric data provides the strongest observational support, yet that the process operates in the regime they described. Before we continue, consider what the observational evidence establishes so far. The black in black hole is wrong, or at least deeply misleading. The boundary region is a synchrotron source. It is magnetized. It is polarized. It varies over time. It contains identifiable structures, hotspots, magnetic flux concentrations, polarization spirals. The darkness at the center of the image is a lensing shadow, not an emission property of the horizon. The horizon may well be causally dark, nothing escapes from inside, yet the environment immediately outside it ranks among the most extreme and diagnostically rich plasma laboratories in the observable universe. Now let us examine the second half of the title, Why Black Holes Are Not Actually Holes. In the classical picture, a black hole contains a singularity, a point or ring of infinite density where the curvature of space-time diverges and the known laws of physics break down. The event horizon surrounds this singularity, and the interior between horizon and singularity is, in principle, empty vacuum space-time for a Schwarzschild black hole, or structured only by frame-dragging effects for a Kerr black hole. The classical interior is not a material object. It is a region of space-time with specific geometric properties. Nothing fills it, nothing structures it. The matter that formed the black hole has, in the classical picture, collapsed to the singularity. The rest is geometry. This picture has been under sustained theoretical pressure for more than 50 years, and the pressure has intensified dramatically in the past decade. The source of the pressure is the black hole information problem, the question of whether information that enters a black hole is permanently destroyed. Roger Penrose's 2020 Nobel Prize in Physics for the mathematical proof that black hole formation is a robust prediction of Einstein's general relativity theory provides the foundation. Yet the classical description he helped establish is precisely what these quantum gravity frameworks challenge. In 1973, Jacob Bekenstein proposed that black holes carry entropy, and that this entropy is proportional to the area of the event horizon, not the volume of the interior. The Bekenstein-Hawking entropy formula makes this precise. S sub BH equals K sub BC cubed A over 4 GH bar. S sub BH is the entropy. K sub B is Boltzmann's constant. C is the speed of light. A is the area of the event horizon. G is the gravitational constant. H bar is the reduced Planck constant. The entropy is proportional to the horizon area, measured in Planck length squared units. For a stellar mass black hole, the entropy reaches roughly 10 to the 77th, a number so large it exceeds the entropy of all the matter that fell in to form the black hole. For a supermassive black hole like M87 star, the entropy grows vastly larger still. The implication is staggering. The boundary carries an enormous state count. The number of possible microscopic configurations consistent with the same macroscopic black hole, the same mass, charge and spin, is exponentially vast. For a solar mass black hole, the Bekenstein-Hawking entropy reaches roughly 10 to the 77th. For context, the total number of particles in the observable universe is estimated at roughly 10 to the 80th. A single solar mass black hole possesses a microstate count comparable in logarithmic terms to the particle count of the entire cosmos. For M87 star, with a mass of 6.5 billion solar masses, the entropy grows incomprehensibly larger. The state count scales exponentially with the area, which scales as the mass squared. In the classical picture, the horizon is featureless. It carries no structure, no hair. The classical no-hair theorem, developed through work by Werner Israel, Brandon Carter, and others in the 1960s and 1970s, states that a stationary black hole in general relativity is completely characterized by three parameters: mass, spin, and charge. Nothing else. No memory of what fell in, whether it was a star, a planet, a library, or a cloud of hydrogen. The end state is the same. The boundary remembers nothing. This is the tension that drives every theoretical framework we are about to examine. An entropy that demands an enormous number of microstates. A theorem that insists the boundary is featureless. A radiation process that appears to destroy the information those microstates should encode. Something is wrong with the classical picture. The question is what? In 1975, Stephen Hawking published the calculation showing that quantum fields in the curved space-time of a black hole lead to particle creation, thermal radiation emitted from near the event horizon. Hawking radiation implies that black holes are not perfectly black, even in the quantum sense. They radiate, and they can, in principle, evaporate completely over cosmological timescales. For a stellar mass black hole, the Hawking temperature is extraordinarily low, of order 10 to the -8th Kelvin, far below the temperature of the cosmic microwave background. Such a black hole would absorb more radiation from its environment than it emits, and would grow rather than shrink. Only after the universe has cooled far below its current temperature, trillions of years in the future, would stellar mass black holes begin to evaporate in earnest. For the supermassive black holes at the centers of galaxies, the evaporation timescale reaches roughly 10 to the 100th years, a number so large that writing it out in full would require more digits than atoms in the observable universe. The principle matters more than the timescale. Hawking radiation is thermal. It carries no information about the specific quantum state of the matter that formed the black hole. The radiation depends only on the black hole's mass, spin, and charge, the same three parameters of the no-hair theorem. If the black hole evaporates completely and the radiation is purely thermal, then the information about the initial state appears to vanish. A pure quantum state, a star with a specific, knowable configuration, falls into the black hole. The black hole radiates thermally. The star is gone. The radiation is featureless. The initial information has no record in the final state. This violates unitarity, the principle that quantum mechanical time development is reversible and information preserving. In quantum mechanics, the present state of a system contains enough information to reconstruct its past. If Hawking radiation is truly thermal and the black hole evaporates completely, this reconstruction becomes impossible. The information has been destroyed. Unitarity is violated. The foundations of quantum mechanics are compromised. Science can describe what happens and how it happens. The question of why these particular laws, why a framework in which information preservation and gravitational collapse appear to contradict each other, exists at all sites beyond the reach of telescopes and equations. The information problem is not merely a technical puzzle. It is a confrontation between two of the most successful frameworks in physics, quantum mechanics, and general relativity, and neither yields. What would you conclude from this evidence? A boundary that carries exponentially vast entropy, radiation that carries no information about what fell in, a singularity that marks the limits of known physics. The classical whole picture, empty interior, featureless horizon, information destroyed, cannot be the complete story. Something must give. The competing proposals for what gives fall into several families. and they disagree at the most basic level about what replaces the classical picture. The Fuzzball conjecture originated by Samir Mathur and developed extensively over the past 2 decades, proposes the most radical replacement. In the Fuzzball picture, the classical event horizon and the interior singularity are both artifacts, consequences of describing gravity with an effective theory that has too few degrees of freedom. When the full string-theoretic description is used, with its additional degrees of freedom, what replaces the black hole is a horizon-sized object, a fuzzball composed of string and brane-bound states, with no traditional smooth horizon and no interior singularity. The object carries structure at the scale of the event horizon. It radiates from its surface like an ordinary body. Information is not trapped behind a causal barrier because no causal barrier exists, only a complex, extended microstate surface. A 2022 multi-author review by Josef Benner, Emil Martinek, Samir Mathur, and Nicholas Warner states the core principle directly. Horizons and singularities arise when gravity is described by an effective theory with insufficient degrees of freedom, and string theory's additional degrees of freedom lead to objects with neither horizons nor singularities. A 2025 review of the Microstate Geometry program, the constructive branch of the Fuzzball program that builds explicit, smooth, horizonless supergravity solutions representing specific black hole microstates, argues that these constructions provide strong computational support for Fuzzball-style resolutions and highlights topology and flux support mechanisms that do not exist in bare general relativity. A 2024 Fuzzball Paradigm Review, co-authored by Madhur Mehta and collaborators, pushes the claim further. Fuzzball microstates, it argues, have no horizon and radiate from their surface like a normal body. Information is not lost because there is no interior to lose it in. The mechanism proposed for why semi-classical physics breaks down even at low curvatures near the classical horizon involves vacuum correlations and what the authors call fast stretching, a process by which quantum entanglement structure is disrupted at horizon scale even when the local curvature is small. The observational question follows immediately. If fuzzballs replace horizons, would we see the difference? A phenomenological study by Fabio Bacchini and collaborators addresses this directly. Using ray tracing calculations through fuzzball geometries, they show that even horizonless microstructure can produce a shadow-like dark region, because the microstructure can trap light on long-lived, highly redshifted chaotic orbits near the would-be horizon scale. The mechanism operates subtly. In a classical Kerr black hole, light that crosses the event horizon is captured permanently, it cannot return. In a fuzzball geometry, no event horizon exists to cross. Light, instead, encounters the extended microstate surface, where it can scatter, reflect, or become trapped in long-lived orbits that circle the object many times before eventually escaping or being absorbed. The resulting image, viewed from far away, looks remarkably similar to a classical shadow, a dark central region surrounded by a bright ring. Potential discriminants exist. A fuzzball, lacking a true event horizon, cannot absorb light perfectly. Some radiation that a classical black hole would permanently capture might instead scatter back from the microstate surface, producing a residual glow, a faint brightness inside the shadow region that a classical black hole would not exhibit. The paper proposes that shadow size and residual glow could, in principle, distinguish fuzzballs from other compact object models. In practice, the current EHT data cannot make this distinction. The shadows are too similar. The residual glow, if present, falls below the current sensitivity threshold. The prediction, though, is specific and falsifiable. Future instruments with higher sensitivity and resolution could test it. The microstate geometry program, the constructive branch of the Fuzzball conjecture, provides the mathematical foundations for these predictions. Microstate geometries are explicit, smooth, horizonless solutions of supergravity, the low energy limit of string theory that includes gravitational and gauge fields. Each solution represents a specific black hole microstate with detailed geometric structure at the scale of the would-be horizon. The structures are supported by topology and fluxes, features of the extra dimensions that string theory requires, and they have no analog in pure general relativity. A 2025 review by Bina, Martinek and Warner argues that these constructions provide strong evidence that the event horizon is not the final word on black hole structure, at least in the regime where supergravity calculations are reliable. The open question is whether the constructions, developed primarily in supersymmetric settings with high degrees of symmetry, extend to the generic, non-supersymmetric astrophysical black holes that the Event Horizon Telescope observes. The gap between controlled mathematical constructions and astrophysical reality remains wide. The firewall hypothesis emerges from a different direction, not from a constructive replacement of the horizon, but from a consistency argument about what happens when quantum entanglement meets gravitational collapse. In 2012, Ahmed Al-Mahiri, Donald Marolf, Joseph Polchinski, and James Sully, known by the acronym AMPS, published an argument that became one of the most discussed papers in theoretical physics. The argument proceeds from three assumptions that most physicists would individually regard as reasonable. First, that black hole evaporation is unitary, information is preserved. Second, that semi-classical quantum field theory is valid outside the horizon. The standard framework of particle physics works in the region away from the singularity. Third, that an observer falling through the event horizon of a sufficiently large black hole would not experience anything unusual. The equivalence principle, a cornerstone of general relativity, predicts a smooth crossing. The problem arises from entanglement monogamy, a property of quantum mechanics stating that a quantum system cannot be maximally entangled with two independent systems simultaneously. Late in the evaporation process, after the page time, the outgoing Hawking radiation must be entangled with the earlier radiation to maintain unitarity. Each outgoing Hawking quantum must also be entangled with its partner behind the horizon to maintain the smooth vacuum state at the horizon, as the equivalence principle requires. The same quantum cannot be maximally entangled with both. Something breaks. One resolution: the entanglement between the outgoing quantum and its interior partner is severed. The vacuum state at the horizon is disrupted. The result is a firewall, a high-energy barrier at or near the event horizon that would incinerate any infalling object. The smooth crossing predicted by classical general relativity would be replaced by a violent high-temperature encounter at the very boundary that classical physics says should be unremarkable. The equivalence principle, one of the most foundational conceptual insights of general relativity, would fail precisely where gravity becomes strongest. A modern conceptual analysis treats the firewall paradox as the sharpened form of the information problem and emphasizes that proposed resolutions often require non-local connections beyond semi-classical causal structure, including strategies motivated by the ER equals EPR conjecture, which posits that quantum entanglement between particles is mediated by geometric connections between space-time regions. A 2024 paper explicitly investigates whether replica wormhole topology, the mathematical structures used in recent information recovery calculations, can generate an AMPS-like firewall via a Dirac delta curvature term and an associated impulse on infalling particles. This is speculative and model-dependent, yet it creates a bridge between two previously distinct resolution families: the Island program and the Firewall program. The smooth horizon may be disrupted not by exotic matter or by string-theoretic microstructure, but by the topology of the quantum gravitational path integral itself. I return to this point often, not for comfort, for clarity. The competing frameworks, fuzzballs, firewalls, islands, are not minor variations on the same idea. They disagree about questions that go to the foundation. Does the horizon exist as a causal boundary? Is crossing the horizon a violent event? Is there an interior at all? These are not details, they are the architecture. The wormhole paradigm and the entanglement island framework offer a third approach. Rather than replacing the horizon with microstructure or a high-energy barrier, the Island program proposes that semi-classical gravity calculations, when they include additional saddle point contributions called replica wormholes, can recover the expected unitary behavior of black hole evaporation. The key result is the Page curve, named after Don Page, who first calculated its expected shape in 1993. The Page curve describes how the entanglement entropy of the Hawking radiation should behave during evaporation if the process is unitary. Early in the evaporation, each emitted Hawking quantum adds to the entanglement between the radiation and the remaining black hole. The entanglement entropy rises. At the Page time, roughly the halfway point of evaporation by entropy, the entropy reaches a maximum and then begins to decrease. Late radiation is entangled not primarily with the remaining black hole, but with the earlier radiation, purifying the combined radiation state. By the time the black hole has fully evaporated, the entropy has returned to zero. The information is encoded in a highly scrambled form in the correlations among the radiation quanta. The Island program reproduces this curve using semi-classical gravity calculations. The mathematical mechanism involves quantum extremal surfaces, surfaces that extremize a combination of geometric area and bulk entanglement entropy. In certain configurations, the quantum extremal surface jumps to include a region behind the classical horizon, an island in the entanglement wedge of the radiation. This jump drives the transition in the entropy curve. Before the Page time, no island contributes. After the Page time, the island dominates and the entropy decreases. The concept is technically precise, but physically puzzling. The island is a region of the black hole interior that, in the semi-classical calculation, is reconstructible from the radiation. Information that appears to be trapped behind the horizon is, in this framework, accessible from outside, not through any signal escaping the horizon, but through the quantum gravitational structure of the state. The mechanism by which this occurs involves the replica wormhole saddle points, additional contributions to the gravitational path integral that connect different copies of the spacetime in a way that has no classical analog. This connection to holographic principles in quantum gravity demonstrates the deep mathematical relationships that have emerged from studying the ADS/CFT correspondence and its implications for black hole physics. A key result from Raphael Bousso and Jeff Pennington makes the implications concrete. They show that the entanglement island, the region included in the radiation's entanglement wedge in semi-classical gravity, can protrude outside the classical stretched horizon scale by a distance of order square root of the Planck length times the horizon radius. For a supermassive black hole, this distance is parametrically larger than the Planck length, potentially comparable to a Bohr radius-like atomic scale. The information theoretic boundary is not confined to an infinitesimal membrane at the event horizon. It extends outward, a quantum halo, not metaphorical, but calculable. Suvrat Raju, in a 2022 review consolidating recent progress on the information paradox, argues that the exterior retains a redundant copy of information that observables accessible from outside the black hole contain, in a subtle and scrambled way, the information about what fell in. The argument is technical, but its implication reaches far. If the exterior already contains the information, then the interior may not be an informationally independent region. The information was never truly trapped behind the horizon in the operationally meaningful sense. It was always accessible, in principle, to sufficiently sophisticated measurements performed from outside. This reframes the information problem. The question shifts from "does information escape the horizon?" to "was the interior ever an informationally separate system?" Raju's analysis provides a counterpoint to Fuzzball and Firewall extremes, a framework in which the horizon remains approximately smooth, the interior remains approximately classical, yet the quantum state of the combined system is such that outside measurements are, in a technically precise sense, sufficient to reconstruct what fell in. The philosophical weight of this claim is considerable. If the exterior carries a redundant encoding of the interior, then the whole, the region behind the horizon that classical physics says is permanently separated from the outside, is not, in the quantum description, a separate system at all. It is entangled with the exterior in a way that makes it reconstructible. The separation is a classical artifact. The quantum reality is more interconnected. A fault line runs within the unitary evaporation camp that deserves explicit examination. A 2021 paper directly contrasts the Fuzzball paradigm with the wormhole/island paradigm. The argument: if one retains semi-classical low-energy dynamics at the horizon in some effective variables, as the island program seems to do, then for the black hole to radiate like ordinary hot matter, one must introduce explicit non-locality linking the black hole and distant radiation. The paper formalizes this via an effective small corrections theorem, a mathematical result showing that small local corrections to the Hawking radiation cannot, by themselves, restore unitarity. The corrections must be large, or they must be non-local. The paper uses toy bit models to illustrate the cost of each choice, and concludes that the wormhole paradigm requires accepting non-locality that the Fuzzball paradigm avoids by simply removing the horizon. This is counter-narrative material of the sharpest kind. Even among physicists who agree that evaporation must be unitary, that information is preserved, the structural disagreement about whether the horizon persists and what it costs to keep it runs to the foundation. The Fuzzball camp says, there is no horizon, problem solved. The island camp says, the horizon persists, but the quantum state carries non-local features that make the interior reconstructible from outside. The Firewall camp says, the horizon persists, but crossing it is not the gentle experience classical physics predicts. 3 camps, 1 question, no consensus. The soft hair program offers a 4th approach, orthogonal in spirit to the others. In 2016, Stephen Hawking, Malcolm Perry, and Andrew Strominger proposed that black holes carry an infinite set of zero-energy soft charges, additional labels associated with asymptotic symmetries known as BMS symmetries, named after Hermann Bondi, M.G.J. Vanderburg, and A.W.K. Metzner, who first identified them in the 1960s. BMS symmetries include supertranslations and superrotations, transformations that act on the boundary of space-time at infinity and that, in the classical theory, were considered physically trivial. The soft hair proposal elevates them to physical significance. These charges do not add energy to the black hole. They do not change its mass or spin as seen from infinity. They provide additional quantum numbers, additional labels that distinguish one black hole configuration from another. The number of distinct soft charge configurations is infinite. The original proposal describes information about the quantum state as stored on a holographic plate associated with the horizon boundary, a two-dimensional surface carrying an infinite dimensional label space. The conceptual leap here is large. In the classical no-hair picture, two black holes with the same mass and spin are identical. No measurement from outside could distinguish them. In the soft hair picture, they are distinguished by their supertranslation charges, labels that record, in some compressed and scrambled form, the history of what fell in. The black hole is not bald. It has hair, but the hair is soft, carried by zero-energy gravitons and photons that populate specific symmetry sectors of the Hilbert space. What soft hair implies for the documentary's core question is this: the exterior boundary of a black hole may not be a featureless absorber. It may be a structured state space, a surface carrying an infinite number of quantum charges that constrain the relationships among outgoing radiation states. Whether soft hair alone suffices to encode all microstate information, whether the infinite charges capture enough detail to resolve the information problem completely, remains contested. The soft charges are conserved quantities. They constrain the Hawking radiation. Whether the constraints are strong enough to fully determine the radiation state is a separate, harder question that the current mathematics has not definitively answered. A 2022 JHEP paper studies how supertranslation soft hair can alter near-horizon geometry relevant to shadow formation and can break the separability of geodesic motion, affecting the very lensing diagnostics that the Event Horizon Telescope uses to characterize black hole images. Soft hair connects symmetry structure to observable imaging features, a bridge between abstract mathematical physics and the data. Albert Huber, in a 2025 paper, derives quasi-local charges constructed using the Brown-York formalism that coincide with soft hair charges in the large sphere limit and outlines an evaporation scenario in which a strictly one-way event horizon never forms. What forms instead is a dynamical or trapping horizon, a quasi-local boundary that can, in principle, allow continuous information and energy escape via these charges. The event horizon in this picture is an idealization. The physically relevant boundary is time-dependent, quasi-local, and not strictly one-way. Xavier Calmet and Stephen Shu contribute a complementary mechanism from effective field theory. Their 2022/2023 work shows that quantum corrections, calculable within the framework of effective quantum field theory, can violate naive classical expectations that exterior fields depend only on global charges. The exterior may carry information about internal structure that classical symmetry arguments, specifically Gauss's law reasoning, say should not be accessible. This is quantum hair in a general sense. The exterior is richer than the classical no-hair theorem predicts once quantum corrections are admitted. We can measure the distances, calculate the masses, map the structures. What set all of this in motion and why these laws and not others remains unanswered. The information problem sits at the intersection of quantum mechanics, general relativity, and thermodynamics, three frameworks that each work with extraordinary precision in their own domains, and that, together, produce contradictions we cannot yet resolve. Now let us return to the observational side, because the data constrains the theoretical proposals in ways that matter. The strongest observational test against a material surface at the would-be horizon comes from the EHT itself. A 2023 EHT metric testing paper for Sagittarius A star explicitly considers alternatives to the presence of an event horizon, a compact object with a surface that absorbs and thermally re-emits, or one that partially reflects. Using the observed image size and the broadband electromagnetic spectrum, the analysis concludes that a thermal re-emitting surface can be ruled out, and that a fully reflective surface is considered unlikely under the class of surface models they evaluate. This serves as a weight on the other side of the scale. Theory demands structure at the horizon. Fuzzballs predict microstate surfaces, firewalls predict high-energy barriers, soft hair predicts additional charges. The simplest surface-like models, objects that absorb and re-radiate thermally, are already observationally constrained. The theoretical frameworks are more subtle than a simple surface, yet the tension is real. If microstructure exists, it must hide well in broadband emission. It must reproduce Kerr-like external signatures to within the approximately 10% accuracy that EHT metric tests currently achieve. The tension sharpens with a specific observation. In the EHT's metric testing analysis of Sagittarius A star, image sizes are found to be consistent with Kerr predictions at this level of precision. If horizon-scale microstructure exists, whether fuzzball surfaces, firewall barriers, or soft-hair-modified geometries, it must produce an external spacetime that is, for all currently measurable purposes, indistinguishable from the Kerr metric. The microstructure must be phenomenologically invisible at the resolution and sensitivity of current instruments. This is not a trivial requirement. A fuzzball surface that radiates like an ordinary body should produce thermal emission. A firewall should produce high-energy radiation. Both should be detectable. The fact that neither has been detected, at least not yet, means either that the theoretical predictions are wrong, that the modifications fall below the detection threshold, or that the way microstructure manifests in observables is more subtle than simple surface models assume. Think about that number. The simplest surface models are ruled out. The sophisticated theoretical models predict modifications that current instruments cannot yet detect. The window between ruled out and not yet detectable is where the next generation of observations must look. What would you conclude from this? The theories demand that the horizon carries more structure than classical general relativity allows. The observations constrain simple versions of that structure. The space between these constraints, the window in which quantum gravitational structure could exist without contradicting current data, is where the frontier lies. Gravitational wave observations provide a different probe entirely. If near-horizon structure behaves like a reflective boundary, a surface rather than a purely absorbing horizon, it should generate late-time echoes after the ring-down phase of a binary black hole merger. The analogy is precise: tapping a bell and listening for delayed repeats. When two black holes merge, the resulting remnant oscillates, rings down, emitting gravitational waves at characteristic frequencies determined by the mass and spin of the final object. If the merger remnant possesses a perfectly absorbing horizon, the ringdown decays smoothly. If instead a partially reflective boundary sits at or near the horizon scale, gravitational waves can bounce between the photon sphere and the reflective surface, producing a series of diminishing echo pulses at regular time intervals after the main ringdown. The echo signal, if detected, would constitute extraordinary evidence for near-horizon structure, a direct gravitational wave signature of a boundary that is not the perfectly absorbing event horizon of classical general relativity. The expected echo delay runs at the order of the light crossing time of the compact object, modified by a logarithmic factor related to how close the reflective surface sits to the horizon, typically milliseconds to tens of milliseconds for stellar mass remnants. Several recent searches using data from LIGO, Virgo and CAGRA's 03 observing run report no statistically notable evidence of such echoes. A 2023 Physical Review D analysis searches for generic secondary transients shortly after binary black hole mergers, targeting a broad set of echo models, and finds no evidence. Upper limits on echo amplitudes are set for individual events. A separate 2023 Physical Review D template-based search across 03 events using different template models similarly reports null results. This does not prove smooth horizons. The absence of echoes constrains the reflectivity of the boundary. If a surface exists, it must reflect gravitational waves at a level below the current detection threshold. The constraints are model-dependent, excluding specific classes of reflecting surfaces with specific reflectivities, not all possible near-horizon modifications. The direction, though, is clear. The simplest, hard surface at the horizon models are increasingly constrained by gravitational wave data, complementing the electromagnetic constraints from the EHT. Raul Carballo Rubio, working with a large collaboration including Matt Visser and Stefano Liberati, published a 2025 community report surveying non-singular black hole models and mimickers. The report maps the theoretical landscape. Regular black holes with resolved interiors, models in which the central singularity is replaced by a finite density core or a de Sitter patch. Horizonless compact objects, gravastars, boson stars, protostars, and other exotic configurations that mimic the external properties of black holes without possessing an event horizon, and various intermediate models that retain some form of horizon but modify its properties. The report catalogues which observational signatures are testable with current and near-future instruments. Gravitational wave echoes test reflectivity. Broadband electromagnetic spectra test thermal surface emission. Shadow imaging tests lensing differences. Ringdown spectroscopy tests the quasi-normal mode spectrum. Tidal deformability tests the internal structure through gravitational wave in-spiral signals. Each signature probes a different aspect of the compact object, and each carries a different sensitivity to different classes of modifications. The conclusion is not that alternatives to classical black holes are ruled out. It is that the observational program is now specific enough to distinguish between classes of models, even if individual models remain degenerate. A gravastar, a hypothetical object with a thin shell of matter at the would-be horizon, supported by an interior of dark energy, produces specific predictions for echo timing and tidal deformability that differ from both classical black holes and fuzzballs. A boson star, a stable self-gravitating configuration of a scalar field, produces a shadow that can closely mimic a Kerr black hole, but with potentially detectable differences in the photon ring structure at higher resolution. Each alternative carries its own fingerprint. The challenge is that current instruments cannot yet read the fingerprints clearly enough to distinguish them. The concept of the event horizon itself deserves closer scrutiny in light of these theoretical developments. In classical general relativity, the event horizon is a global concept. Its location depends on the entire future history of the spacetime. You cannot determine at any given moment whether you are inside or outside the event horizon without knowing the entire subsequent causal development of the universe. This is not a minor technicality. It means the event horizon is, in a precise physical sense, teleological, defined by what will happen, not by what is happening now. Modern alternatives focus on quasi-local horizon concepts: apparent horizons, trapping horizons, dynamical horizons. These are defined by local conditions, specifically by the expansion rate of outgoing light rays at a given moment. A trapping horizon forms when outgoing light rays, despite being directed outward, are being focused inward by the curvature of space-time. These quasi-local definitions can exist in dynamical settings without requiring knowledge of the entire future. They can form, shift, and, in certain circumstances, shrink or disappear as the space-time changes. Albert Huber's 2025 work on dynamical horizon soft hair exploits this distinction. If the physically operative boundary is a dynamical horizon rather than a strictly one-way event horizon, then information and energy escape becomes conceptually possible. The event horizon, in this picture, is an idealization that the full quantum gravitational description may not require. Near-horizon flare physics provides a final observational vignette. A 2024 Nature Astronomy study describes flares from Sagittarius A star as a frontier topic, discussing hotspot and flux tube models tied to magnetic reconnection near the innermost stable circular orbit. These are compact, transient emission structures, not the passive absorption of a featureless boundary, but active plasma processes occurring within a few gravitational radii of the compact object. Even around a low-luminosity supermassive black hole, Sagittarius A star accretes at a tiny fraction of its Eddington luminosity. Active, structured, magnetized phenomena exist at the boundary scale. For those who value going deeper into these frontier topics, our Patreon supporters help make this level of research possible. The link is in the description. Let us now take stock of what the evidence file contains. The word black fails. The boundary region of a black hole is a synchrotron source. It is magnetized with field strengths of 1 to 30 Gauss inferred near M87 star. It is polarized with spiral E-phi PA patterns, circular polarization detections, and peak fractional polarization of 40% near Sagittarius A star. It varies over time with multi-epoch changes in polarization morphology and intensity distributions for M87 star and 70-minute polarization rotation periods from orbital hotspots near Sagittarius A star. The ring diameter of M87 star holds stable at 43.9 plus or minus 0.6 micro-arcseconds across years, yet everything else about the emission changes. The darkness at the center is a shadow, a photon capture feature, not the signature of a silent absorber. The word hole fails. The classical picture of an empty interior behind a featureless horizon is challenged by every major quantum gravity framework currently under development. Fuzzballs propose horizonless microstate structure at horizon scale. Firewalls propose high-energy barriers that would destroy any infalling object. Entanglement islands extend the information reconstruction region calculably beyond the classical horizon. Soft hair endows the boundary with an infinite set of quantum charges. Quantum hair from effective field theory violates classical no-hair expectations. Non-singular models replace the interior singularity with regular geometries. No single framework has achieved consensus. The convergence of their implications, though, is unmistakable. The smooth, empty, featureless interior of the classical black hole is incomplete. Some questions may simply be beyond what science alone can address. Which assumption fails? Locality, semi-classical quantum field theory near the horizon, or the smoothness of infall? If microstructure is real, why does the exterior look so Kerr-like across mass scales? Where is the information stored? On a holographic plate of soft charges in island regions outside the horizon, distributed across a fuzzball surface, or in some framework not yet conceived? These are questions whose answers require not just more data, but a deeper theoretical framework, one that unifies quantum mechanics and gravity in a regime where both are needed and where neither alone is sufficient. The Event Horizon Telescope continues to observe, with next-generation upgrades planned to add new stations and extend to shorter wavelengths, increasing both resolution and sensitivity. The transition from static snapshot to continuous monitoring is already underway, as demonstrated by the multi-epoch M87 star variability analysis. ALMA, on the Chajnantor Plateau at 5,000 meters elevation in the Atacama Desert, provides the highest sensitivity single-dish anchor for the EHT array and enables standalone polarimetric monitoring of the kind that detected the SagittariusA star hotspot. Gravity at the Very Large Telescope Interferometer, the European Southern Observatory's flagship interferometric facility, which combines multiple telescopes as a virtual aperture for near-infrared observations, tracks flares from SagittariusA star with micro-arc-second precision. Gravity reported first light in 2015 and has provided some of the highest precision constraints on the mass and orbit dynamics near the galactic center, including the detection of gravitational redshift in the orbit of the star S2, passing within 120 astronomical units of Sagittarius-A star. The Imaging X-ray Polarimetry Explorer, IXPE, launched on December 9, 2021, adds X-ray polarimetry to the multi-wavelength observational program. X-ray polarization probes different emission mechanisms and different regions of the accretion flow than millimeter-wave observations. The Comptonized emission in the X-ray corona, the reflection signatures from the accretion disk, and the jet emission at its base. The Chandra X-ray Observatory, launched July 23, 1999, and still operating after more than a quarter century, provides high angular resolution X-ray imaging and spectroscopy. NuSTAR, the Nuclear Spectroscopic Telescope Array, launched June 13, 2012, extends the X-ray coverage to hard X-rays, probing the innermost accretion flow through ion line emission and Compton reflection. LIGO, Virgo, and Kagra continue to search for gravitational wave echoes in merger remnants, with each observing run improving the sensitivity to near-horizon reflectivity. The planned next-generation gravitational wave observatories, the Einstein Telescope in Europe and Cosmic Explorer in the United States, will improve sensitivity by an order of magnitude, potentially bringing echo signals within detectable range if near-horizon reflectivity exists at the levels currently consistent with upper limits. Each instrument probes a different aspect of the boundary, Each narrows the space of allowed models. None by itself resolves the question. The convergence of electromagnetic observations across wavelengths, gravitational wave searches, and theoretical constraints from multiple frameworks creates a web of evidence that is tightening around the central question. What is the boundary of a black hole? Karl Schwarzschild's equation, R sub s equals 2gm/c², converts mass to a length scale. Bekenstein's entropy formula, S sub bh equals k sub bc cubed a over 4gh bar, converts that length scale to a state count. Hawking's radiation converts that state count to a thermodynamic crisis. Mathur's Fuzzballs, the AMPS Firewall, Hawking-Perry-Strominger's soft hair, Busso and Pennington's islands, each attempts to resolve the crisis in a different architecture. The Event Horizon Telescope, ALMA, Gravity, IXPE, LIGO, each tests the resolution against data. Black holes are not black. The boundary region is a structured, magnetized, time-variable synchrotron source whose polarization encodes the magnetic and plasma conditions within a few gravitational radii of the compact object. Black holes are not holes. The classical picture of a featureless horizon around an empty interior is under sustained theoretical pressure from frameworks that demand structure, microstate surfaces, energy barriers, charge distributions, extended information reconstruction regions at the scale of the would-be horizon. What they are precisely remains the question. The observations constrain. The theories propose, the data accumulates, the debate continues. The Schwarzschild radius defines a scale. The Bekenstein-Hawking entropy implies a state count. The information problem demands a resolution. The Event Horizon Telescope measures the environment. The competing frameworks, fuzzballs, firewalls, soft hair, islands, map the theoretical landscape. The boundary of a black hole, whatever it ultimately proves to be, is neither black nor a hole. It is something we do not yet have a name for, something the data is beginning to reveal and the theory is still struggling to describe. Not tragic, not triumphant, just unresolved. Good night.